Now hopefully you remember polynomial functions have end behaviors dictated by their leading terms. When we look at ratios of polynomials, it's the same sort of idea, but you've got a polynomial on top and a polynomial on the bottom. So you basically find the leading terms of each of those and then simplify that ratio to see what happens. So the concept here is not much different for rational functions versus polynomial functions, but there's a little more simplification and there are some different leading terms that can result. So we're going to look at those now. So when you simplify the leading term of a rational function, you could get the same leading term that you did with a polynomial. So we'll recall those now. So if you end up with a positive x to an odd power or a positive x to an even power, remember that when you have x to a power, the ends will grow. They'll go up in the positive direction or down in the negative direction, etc. So these ends grow, okay? I want to point that out because when we get to some new end behaviors, they won't necessarily grow. But if you have x to a power, they will grow. If you have x to an odd power, it's going to grow in the negative direction on the left and in the positive direction on the right. If you have x to an even power, it's going to grow in the positive direction on the left and also the positive direction on the right. They both ends are growing, going to positive or negative infinity. And we also know what happens if you multiply by a negative coefficient. You simply flip those over. I'm not going to go into that just yet. Now, the new end behaviors that you could get for a rational function when you simplify, you could end up with more x's on the bottom. So you could end up with a positive coefficient times 1 over x to an odd power. When you simplify, you're either going to cancel all of the x's on top or all of the x's on bottom. Okay, so if all the x's on top disappear, you're going to be left with more x's on bottom. So you could end up with x to an odd power on bottom, or you could end up with x to an even power on bottom. Okay, now when that happens, as x goes to infinity, if you're dividing by, because x is on the bottom here, if you're dividing by a really big number, you're going to get a really tiny number. So these ends do not grow. These ends shrink or approach 0. They shrink. Okay? So when you divide by x to a power, the ends shrink. If you've just got x to a power, the ends grow. That can help you tremendously. Now, if you're dividing by x to an odd power, both ends are going to shrink to 0. Now, the left end is going to approach 0, but it's going to get closer to 0 from the negative side. So it's going to come up like this from the negative side and get closer and closer to this x-axis. Okay? And on the right side, it's going to get closer and closer to 0, but from the positive side. Okay? Now notice the odd power here, whether it's x to an odd power or 1 over x to an odd power, the left side is negative, and the right side is positive for the x to the odd powers. Whether you have x to an odd or you're dividing by x to an odd, the left side is negative, the right side is positive. When you're dividing by x to an odd, though, the ends are going closer to 0, while x to an odd, both ends are growing to infinity. Okay? So I bet you can guess what happens when you divide by x to an even power. Both ends are going to get closer and closer to 0, but on the left side, it's going to get closer and closer to 0 from the positive direction, like this. And on the right side, it's going to get closer and closer to 0, also from the positive direction. So notice the even powers are positive on both ends, whether they grow or approach 0. Okay? So if you're dividing by x to a power, the ends shrink. If you're not dividing, the ends grow. X to an odd is negative on the left, positive on the right. X to an even is positive on both ends. Okay? Now again, if you have a negative coefficient, all you do is you flip these over the x-axis. So if this is a negative x to an odd, we know that it's positive, negative. If it's negative x to an even, both ends are negative. If it's negative 1 over x to an odd, well, the left side is going to be positive and the right side is going to be negative. And if it's negative x to an even, the left end is negative and the right end is negative. So I don't like to think of the negatives as being completely different end behaviors. It's just the end behavior flipped over the x-axis. Okay? So the last end behavior for rational functions is when all of the x's on top cancel with all of the x's on bottom and there are no more x's. When that happens, you simply get a constant, like c. And so whenever you graph a constant function, it's just a horizontal line, okay? So what you have here is you locate that constant. It can be positive or negative. You locate the constant on the y-axis. So let's say it's right here. And both ends get closer and closer to that constant, like this. You get horizontal end behavior, okay? Now, what's happening is you're actually getting closer and closer to this constant. So you might be getting closer to it from the top side or the bottom side. We don't really care. You're getting closer and closer to that constant on both ends. That's what we call a horizontal asymptote. An asymptote is a line that your graph gets infinitely close to. So this horizontal asymptote is the y value of your constant c. That could be 5, for example, y equals 5. Now similarly, when we look at the ends that approach 0, that's also a horizontal asymptote. You can see our graph is getting infinitely close to this horizontal line. So this is a horizontal asymptote also, but it's y equals 0 specifically because your graph's getting infinitely close to 0. And the same thing is true over here, a horizontal asymptote of y equals 0. These guys up here have no horizontal asymptote because we're not getting infinitely close to a horizontal line. Okay, let's do some examples where we find the end behaviors of rational functions. So here we have a ratio of two polynomials, 2x minus 3 over negative 5x plus 1. And so what we need to do is look at the leading term on the top and the bottom. So on the top, our leading term is 2x, and on the bottom, our leading term is negative 5x. And so so here's the new part with rational functions. You get the leading terms for the top and the bottom, and then you have to reduce or simplify that fraction. And so in this case, the x's cancel, and we just get a constant of negative 2/5. So this is a constant. There's no x's left. All the x's canceled. And so our end behavior, we locate negative 2/5 on the y-axis, which is right here. And we get this horizontal asymptote, and our graph is going to approach that horizontal asymptote of negative 2/5 on the ends. And so that's our end behavior. As x goes to negative infinity, y approaches negative 2/5. As x goes to positive infinity, y also approaches negative 2/5. Here our function is 3 times x minus 1 squared over x plus 4 to the 4th times x minus 5 to the 3rd. Now, just like with polynomials, we have to simplify to find our leading terms. So if we multiply out everything on top, we're going to get 3 times x squared for our leading term. On the bottom, if we multiply all of this out, we're going to get x to the 4th times x to the 3rd for our leading term on bottom. Then we have to reduce this or simplify it. So we're going to get, let's say, equals, so we get 3x squared over x to the 7th power. And when we simplify that, the 2 x's on top will cancel with 2 of the x's on bottom, leaving 3 on top over x to the 5th. Okay? So that's the same thing as the constant of 3 times 1 over x to the 5th. I just like to separate off my coefficient here, which is a 3, so that I can see if it's positive or negative, and I can see that the focus of my end behavior is going to be the 1 over x to an odd power. 1 over x to an odd power gets closer and closer to 0. So our graph is going to have a horizontal asymptote at y equals 0, and it's dividing by x to an odd power, so the left side's negative, getting close to 0, and the right side's positive, getting close to 0, and that is the end behavior of this function. h of x equals 4 minus 5x over x plus 1 cubed. Well, the top is already simplified. We just have to locate the leading term, which is negative 5x. 4 has a lower degree, so negative 5x is the leading term on top. On bottom, we have to multiply out x plus 1 times x plus 1 times x plus 1, whose leading term would simply be x to the third power. And if we simplify that, we cancel the x on top with one of the x's on bottom, we get negative 5 over x squared, which is the same thing as negative 5 times 1 over x squared. Now, because our leading term simplifies to give us 1 over x to a power, the ends are going to approach 0. So again, I'll have a horizontal asymptote at 0, and 1 over x to an even power, both ends are positive. But I'm multiplying by a negative, so both ends are going to flip over and be negative. So I need to approach 0 from the negative side on both ends as x goes to negative infinity and as x goes to positive infinity. All right, so we've got 3x to the fourth plus 5x cubed minus 2x squared plus x minus 7 over negative 2x squared plus 5x cubed minus 8. Now, luckily, we don't have to do any simplifying to find the leading term. We don't have to multiply anything together. So on top, the leading term is the highest power, so that's 3x to the fourth. And on bottom, the leading term is the highest power, so that's positive 5x to the third. Now this time, I have more x's on top. So the 3 x's on the bottom will cancel with 3 of the x's on the top, leaving an x behind on top. So we get 3x over 5, which, if I separate the coefficient, is the same thing as 3/5 times x to the first power. I have more x's on top, not on bottom, so I'm not dividing by x to a power. That means our ends are both going to grow. Okay, x to the first power, on the left end, it's a straight line that grows in the negative direction, and on the right end, it's a straight line that grows in the positive direction. Okay, the ends are growing, not shrinking to 0. And notice I didn't flip this over because my coefficient here is not negative. It's a positive 3/5. So here we've got negative 5x cubed times x plus 4 to the 7th over 9x minus 1 times x plus 3 to the 9th. On top, if we multiply all of this out, I'm going to have my negative 5x cubed, and then x plus 4 to the 7th, if I multiply all of that out, I'm going to get x to the 7th as my leading term. On the bottom, I get a 9x for my leading term of 9x minus 1 times x plus 3 to the 9th. If I multiply all of that out, the leading term is x to the 9th. So now I'm going to simplify this. On the top, I get negative 5x to the 10th power as my leading term, and on the bottom, I get 9x to the 10th power as my leading term. In this case, the x to the 10ths cancel out completely, leaving behind the constant of negative 5/9. And so what I end up with is negative 5/9 on the y-axis, gives me a horizontal asymptote there. And my end behavior is approaching that line. I don't care if it's above or below necessarily, but it's getting infinitely close to that horizontal asymptote of y equals negative 5/9. That's our horizontal asymptote. So there are several examples with end behaviors of rational functions. It can be overwhelming, but go back and watch my summary at the beginning of the video if you need to about how to determine if the ends grow or shrink, and whether the left side's negative or positive, whether the right side's negative or positive. It'll help tremendously. Make sure you learn these and that you're not looking them up.